I'm Ken, the Metal Professor. It is too cold outside to do anything useful there, so I'm going to sit indoors and solve a couple of u-substitution problems. These appear early on in the kind of standard Calc 2 sequence, at least in the United States, so some people might be encountering these. U-substitution is a game where you take an integral, look at it, and say, ooh, this looks difficult, and you change the variable in a strategic way so that what looks like a harder integral shrinks down to become a recognizable, simpler integral. And the trick to u-substitution is a little bit of pattern recognition. It's to look in the function that you are supposed to integrate, the integrand, and see if you can spot a little function and something that looks like the derivative of that little function. If you can spot that pair of things, you're off to a good start. Now, by looks like, I mean that if you've spotted a little smaller function inside the big function, and there's something else in there, in that soup of letters, that is exactly the derivative or different by a multiplicative constant, that's the link you're looking for. So as an example, I will show you this one. The integral from -5 to -2 of x plus 4 times e to the x squared plus 8x plus 12. Now, when you look at this, I've highlighted the x squared plus 8x plus 12 in red. That function's derivative is 2x plus 8. Now, the other stuff in the integral, I don't see a 2x plus 8, but I do see an x plus 4, which is half of 2x plus 8, or other words, if we took x plus 4 and multiplied it by 2, we would have 2x plus 8. So we do in fact see a function in here as well as something that's off by the derivative by a multiplicative constant, and that's how we latch onto this for our substitution, to take this messier thing and convert it to something that's a little bit simpler. So we will assign, this is why it's called u-substitution, u is going to be equal to the parent function of these two things we've spotted. So x squared plus 8x plus 12. Okay? And then the derivative of this thing we just assigned as u. Now forget the integral for a minute. It's just we've said u is equal to x squared plus 8x plus 12. Given that choice, du dx, its derivative, would be 2x plus 8. Okay? Or, a little bit of rearrangement, du is 2x plus 8 times dx. Or that's equal to 2 times x plus 4 dx. All right, and now we know how we're going to substitute that x squared plus 8x plus 12. That's just going to be u, and then the x plus 4 dx is going to end up being 1/2 a du. And once we make, once we make this substitution, the new integral to solve is going to be simpler than the one that's originally presented. Now, we have a choice here because this is a definite integral. Some people will leave the limits alone, will carry out the new and simpler integral that's come about by substitution, and then undo the substitution to return to the original variables, and then plug these in. And the dog is barking because somebody across the street's pulling into their driveway every time I start a video. Okay, the car across the street is in the garage, the dog has stopped barking, and that gave me an opportunity to rewrite the integral that we are doing. Remember that the exponent x squared plus 8x plus 12 is what we called u, and this x plus 4 dx is what we determined was 1/2 of du. And before I was rudely interrupted by our dog, we were thinking about what do you do with these limits. Okay, so like I said, some people leave them alone, carry out the integral of this simpler function in terms of u, and then reverse the substitution back to x, then plug in the limits. I think a better way to do it is just go ahead and completely transform the integral into terms of u and then you don't have to worry about reversing the substitution. So remember, these limits of integration are values of x. When x is -5, then u, since we made the substitution, u equals x squared plus 8x plus 12, u would be -5 squared plus 8 times -5 plus 12. Yuck. That would be 25 minus 40 plus 12. Good grief. That would be 37 minus 40, so that's -3. And then when x is -2, the u value that goes with that is -2 squared plus 8 times -2 plus 12. And I'm running out of room down there at the bottom, but that is 4 plus 12, 16 minus 16, so that's a big fat 0. So the new integral is going to go from -3 to 0. So I'm going to flip the page digitally. Let's remember, this lower integral bound is now going to be -3. This upper bound is going to be 0. This mess is going to be e to the u, and then this is just 1/2 du. So we'll have integral from -3 to 0. Was it -3 or -2? I've already forgotten. -3. Okay, good. And then e to the u times 1/2 du. What do we do with that 1/2? Well, we factor it out. Like so. And then we get to integrating. The antiderivative of e to the u is e to the u. And now we're going to plug in -3 and 0. Again, we don't have to go back to the original variables, the original limits. We've transformed everything. And so this, by the fundamental theorem, is going to be e to the 0 minus e to the -3. Like so. And if I simplify that, e to the 0 is 1. So 1/2, oops, I'm getting off the bottom there. And well, if you want to write that as 1 over e cubed, go ahead. Sorry, I blew off the bottom of the page down there. 1/2 times 1 minus 1 over e cubed. Do not go grab the calculator and type that in to try to get some rounded decimal. This is the perfect answer. Well, let's see if it's the perfect answer. Let's go back to WebWork here and try to get that Pavlovian response of a perfect answer. Let's see. Oops, parentheses, fix. And there we go, fix. And we can preview the answer just to make sure it's entered the way, okay, and it's off the screen for you, but I can see that it looks the way I want it to look. Check my answer, and it is correct. That nice green shows up. Feel the relaxation. All right, let's go to another problem. Okay, here's a second problem that's going to show a slightly different usage of u-substitution. The general u-substitution scenario is to try to simplify an integral by playing spot the derivative. We see in the big function we're trying to integrate, we see a small piece of it that if we let that be a new function, we also see the derivative of that function in there, in the integrand, or something close to it, meaning off by a multiplicative constant. That's the previous problem. That's the, sort of the ground level u-substitution. Now, substitution has other forms, other uses, perhaps just to rearrange an integral from something that's a little grosser to a new version of it. For example, this one, we're integrating x times the square root of 25 minus x. And for this, it would be great to use a power rule type of integral for this because of the square root, but it's not quite going to work because the x appears inside and out, and we can't take that x on the outside and multiply it through. Or we could multiply it under the square root, but that's just going to make things worse. You look at this and you think, boy, I wish that was just the square root of a single variable, because then maybe I could multiply that out with other terms, and that is the key here. So what I'm going to do is just turn this thing inside out with a substitution. So I'm going to let u, I should make you see that, that would help, right? Okay, so we're going to let u be that 25 minus x under the inside. Now du in this case is going to be negative dx. The limits of integration, when x is 0, that top limit, u is going to be 25 because u is 25 minus x. Okay, and the lower limit when x is negative 11, u is going to be 25 minus x, so 25 minus negative 11, that will be 36. And so we can recast this integral as the integral from 36 to 25. Now don't automatically put the larger value on top, you have to put them in the place of their corresponding x limits. X, well, what is x? X is going to be found from here. We're turning all the x's into u's. If u is 25 minus x, then x is 25 minus u. And the square root of 25 minus x is now just the square root of u, and that is why we did this substitution. Oops. And dx, that's in the original integral, is negative du coming out of the substitution statements there. Okay, and what that negative sign is going to do is let us flip the limits of integration around so that the larger one is on top as we would like. I mean, it's not necessary to do that, but it certainly helps. So I'm going to flip the page and rewrite this as the integral from 25 to 36 of 25 minus u times the square root of u du. This version of the integral is much preferred to the other one because this is the integral from 25 to 36 of 25 square root of u minus u square root of u du. And each of those terms can just be integrated with a power rule. So let's make that explicit. 25u to the 1/2 minus u to the 3/2 du. Okay, and the antiderivative of these things, 25, remember power rule, add 1 back to the exponent, divide by that new exponent, and u to the 5/2 divided by 5/2, and we're going to evaluate that from 25 to 36. Okay, I'm going to flip the page again, and I'm also going to take those denominators of the 3/2 and 5/2 and invert and multiply for this new expression. So I will get 2/3 times 25 times u to the 3/2 minus 2/5, let me go gather this again, u to the 5/2 Did I collect everything I needed to? Yep. And we're going to evaluate that from 25 to 36. This is going to be gross, okay? Because there's no simplification with the 2/3 and the 25 or the 2/5 over there. So we're just going to plug in 36 and 25 into this mess. Let me simplify these things separately. When u is 36, the value we're going to get is 2/3 times 25 times 36 to the 3/2, which is the same thing as 2/3 times 25 times 36 to the 1/2 cubed. Now, why did I do that? Well, that's because this is just 6. So we'll get 2/3 times 25 times 6 cubed. This number is very, very large. I could simplify probably with this 3 a little bit if I wrote 6 as 3 times 2, and I could do a little cancellation, but yeah, you know, maybe what I'll do is this, 75. Sorry, nope, that's wrong. I was about to get excited that I could do cancellation, but that's because I miscalculated. 50 over 3 times 6 cubed. Okay, when I go plug in 25 for u, should I do that on this page or should I flip the page? I'm going to flip the page here. If there was a slight jump there, it's because I paused the video to write down that expression on a piece of paper just to make sure I didn't mess it up when going from page to page. Okay, this is what we're working with, and we're about to plug in 36 and 25 and subtract those two results. Yick. But we're stuck with it. We will persevere. So, first of all, let's recognize that u to the 3/2 is u to the 1/2 cubed, okay? And u to the 5/2 is u to the 1/2 to the 5th. And remember that u to the 1/2 is the square root of u. So it's nice that these endpoints just happened to come out to be perfect squares. So in fact, what I'm going to do here is I'm going to gather this information separately. I'm going to plug in u equals 36 to this mess. And I'm going to get 2/3 times 25 times the square root of u cubed. So when I'm plugging in 36, square root of u is 6, 6 cubed, then minus 2/5 times the square root of u to the 5th. That'll be 6 to the 5th. Can I do anything with this? Well, I can factor out a 2. I can factor out a 6 cubed and leave behind a 25 over 3 minus 1/5 times, and factoring out a 6 cubed there will leave 6 squared, and I'll just write that as 36. How about that? Okay, and then when u is 25, I'm going to get, for the yucky thing up here, 2/3 times 25 times u to the square root of u cubed. Square root of 25 is 5. 5 cubed is the result, minus 2/5 times the square root of u to the 5th. Square root of 25 is 5, so 5 to the 5th. And then comparing that to the previous result, that looks about right. And so again, also I'm going to plug in 2 times 5 cubed, leaving behind, let's see, 1/3, another 25/3, minus 1/5 times 5 squared, there's 25. Whew. Okay. And now we have to subtract these two results, because remember, we are working on the fundamental theorem of calculus, and we are plugging in the endpoints of 25 and 36 and subtracting. So 2 times 6 cubed times, come on, go back there, 25/3 minus 36/5. Minus, that was the result from u equals 36. And now 2 times 5 cubed times 25 thirds minus 25 fifths. Ick. Okay, that is our result. Now, why am I doing it like this? Because I want to show you that it's perseverance, man. Ladies, you've just got to grit your teeth and follow through with the algebra to get to this net result. And again, I suppose we could type it into a calculator and get a decimal approximation, but this is the best version of the answer. Everything is exact. So I'm going to slide this out of the screen so I will be able to see it. You won't be able to see it. And I'm going to type this monster into this answer box. Again, because it's fun. Whoops, no, that's not what I want. 25 thirds minus 36 fifths. It's good to get your answer confirmed. And I also want to stress that if you are working with WebWork or many other computer algebra systems, they should be good at recognizing equivalent answers regardless of how they are entered. I could have factored a 25 out of there. What do you know? Is there a parentheses on the bottom of that? Okay. Is that what we had? Cross your fingers. Yes, it is correct. It is a huge mess. It's awful, but it was correct. Again, that green that shows up in WebWork at least. Awesome stuff. That was no fun, but I'm going to do another problem. Last one. Okay, final problem. Put here for a couple of reasons. One is to introduce trig functions, to change the variable so that you see that the process is the same. It doesn't matter whether it's dx or dt or dq or whatever. You want to know the process. Don't get too hung up on the details. And a little bit of extra substitution strategy will be in play here. So like in the first problem, we're going to play the game, well, even in the second, but this one more so. We're going to play the game of spot a function and its derivative, or at least something that's equivalent to the derivative up to a multiplicative constant. And so in this problem, which hopefully I've written down correctly, -4 cosine 7t over 10 plus 3 times sine of 7t to the 4th. Okay, I've highlighted the sine of 7t and cosine of 7t. You know, each one's derivative is a multiplicative constant of the other, so which one becomes useful for the substitution? Well, if we let u equal cosine of 7t, then the thing that we're going to hope turns into du is down in the denominator, and that doesn't do any good. The du needs to be up in the numerator. So our process will begin with a recognition that u is going to be based on sine of 7t. Now you'll notice that I've left a little bit of space there, okay? Because when you're making a substitution, you might as well cast as wide a net as possible as long as the substitution still plays out correctly and completely. So sure, the derivative of sine of 7t is within a multiplicative constant of cosine 7t. But let's think bigger. What if I put that 3 in there as well? Let's say u is 3 times sine of 7t. The derivative of that would be within a multiplicative constant of cosine of 7t. But let's think bigger. How about we put in that? Because the derivative of 10 is 0, right? So if I cast my net as wide as possible and let u be the entire inside of that 4th power in the denominator, then du for that substitution, well, 10's going to turn into 0 with its derivative. 3 sine of 7t's derivative is 3 times 7 times cosine of 7t dt. Okay, or the cosine of 7t that's waiting up there in the original integral to be substituted for is du over 21, that 3 times 7. So when I complete this substitution, my new integral is going to be the integral of -4 times the cosine of 7t is du over 21. I'm going to go ahead and put that 21 in the denominator. And the denominator that used to be 10 plus 3 times sine of 7t to the fourth, that's just u to the fourth. So we clean this up quite a bit. And I'm even going to factor out the -4 over 21 when I get to the next screen. Come on, u. There we go. So that'll be -4 over 21, integral of, well, du over u to the fourth, that's u to the -4th du. Okay. Whew, this is just a good old-fashioned power rule. So -4 over 21, antiderivative of u to the -4th is u to the -5th? No. Right? Remember, when you're working with negative exponents, you have to be a little bit more careful. The antiderivative of u to the +4 would go up to a u to the 5th with a multiplicative constant. You always add one back to the exponent when you're doing an antiderivative. When the exponent is negative, the process of adding one back to it moves it which way for you? It moves it in the positive direction on the number line, which actually produces a number that's smaller. The antiderivative of u to the -4th is u to the -3rd, but then, as always, divide by that new exponent. And then plus c. And then those minus signs cancel. So how about we get 4 over 3 times 21. I mean, I can keep writing it as 3 times 21, or I can just make it 63. Maybe put that u cubed back underneath. Okay, and then we have to revert to the original variable, which is different than just trading u back for x. We have to remember what our substitution was. This will be 4 over 63 times, remember our substitution was u equals 10 plus 3 sine 7t all of that cubed plus c. Okay. Again, the story here was to cast as wide a net as possible while still doing everything correctly for the substitution to turn that entire denominator into u to the 4th. All right, I've moved my written page off to the side so I can see it while I'm typing it in. 4 over 63 times 10 plus 3 times sine 7 times t cubed plus c. I put in my multiplications explicitly just to make sure that there's no confusion over what's what. Okay, I'm double checking back and forth. 4 over 63, 10 plus 3 sine 7t cubed, 10 plus 3 times 7t cubed. Okay, cross your fingers. Yes, green. Green is good. All right, so that was a round through, longer than I thought, but what the heck. 3 u substitution problems, a standard one, throwing in some limits of integration. What do you do with those in this story here of cast as wide a net as possible? Hope it helped. My next video in a day or two, I will jump up to some early Calc 3 type of problem, and then I'll circle back around to Calc 1.